Welcome back to Conquering the JavaScript Interview. And we're going to continue my Bitwise Basics series here by exploring another very cool algorithm that we're going to be exploring in this video. The air quotes will make sense here in a minute if the thumbnail and title haven't already given it away. I've got a real treat for you. I'm tackling a question that's as intriguing as it is fundamental. How do computers add numbers at the most basic level? And because this is the Bitwise Basics series, you're already thinking something with bitwise operators and binary arithmetic, and you are correct. We are exploring how to add two integers together without using the addition operator, aka our lovely plus sign. This episode is not just about the coding challenge, it's honestly understanding something at the core of computing. But before we jump in, check the description down below for our Covalence community membership. For $25 a month, you get access to our entire full stack program, broken apart into a front-end and back-end course, which is over 300 hours of content, lectures, walkthroughs, drills, and labs. They're going to get you to either sharpen your skills or get you from zero to hero. Speaking of zero to hero, I also have a comprehensive React course that I continually update and cover a whole bunch of concepts and deep dive a whole bunch of stuff. So if you like my attitude, my passion for teaching and coding, then check out our membership link down below in the description. And the best part is that you get all future course updates, because with as fast as React and technology for state management and things like that can move, I try and keep things updated all the time, as well as in our full stack course. Any new course additions as well. All those updates, any new additions, for free, added to you. Don't have to pay any extra for things like that. And you'll also get access to our Discord, because let's be real, having a supportive, fun community to learn in is much better than getting flamed in a Reddit thread. So now we're going to dive into the world of bitwise operations and see how we can add numbers together without the trusty addition operator. So grab your coffee if you need one, and let's get coding. So the problem here, this is about as simple as a problem can get. This is way more fluff text than it needs to be here. But this is a simple question. How do computers add numbers at the most fundamental level? Right? So we're going to add two numbers together with a function. For example, add without plus. And it's going to take two inputs, which are going to be two integers, and it needs to return their sum. If you add 5 and 3, you get 8. It's pretty simple. But remember the twist, the trick. The requirement here is that you can't use the plus sign. You can't use the addition operator because this is stupid simple with it. In other videos, I've shown the non-bitwise way to solve something, and I don't think I need to do that here because we would just return A plus B. It's pretty simple, right? So that is our problem, right? Take two numbers, add them together without a plus sign. So it gets to the heart of how computers perform basic operations. So again, this is not just a trick. It is foundational computer science. I love this little series I've done here. I've learned so much about binary and computers and how they work at a fundamental level by doing these videos for y'all. And I hope y'all are having as much fun as I am, because truly, I've had so much fun DMing all my friends all the goofy stuff I've been figuring out. So like I said, for once, our algorithm is extraordinarily straightforward. The inputs are very obvious, two integers. It needs to return the sum of those two integers, so it's very easy to know if the answer is right or wrong, which the code is also not bad if you understand it. And as always, I'll do like a breakdown commentary style of how it works. So yeah, function is straight up. I'm going to go ahead and copy this so I can just write it really quickly. The inputs are straightforward. The output is straightforward. The code in between, not so much until you see it. So let's get going. As always, I'll have this available in a CodePen. I'll have my diagrams link with Imgur links available down below as well in the description, so you can pull out the diagrams to help remind you how these binary operations work. And as a dead giveaway, considering I have these three diagrams of AND, XOR, and left shift, I think you know which ones you might need to solve this. Now, I do advise that even if you have no clue what's going on and you copy the CodePen on over, to follow along and code with me and try and writing things out yourself, as that will gain you so much more understanding than just copy, pasting, and staring at code I've written for you. So here we go. We're going to write a function called add without plus. It's going to have two parameters, an A and a B, for the two numbers we need to return together. Now again, the code without bitwise, I said I wasn't going to write it, but I did. That's it. That's all you need to do with that at Bitwise. That's nothing to it. I feel like I shouldn't need to explain this. Now, let's get very fancy. So we need to convert these numbers clearly to binary, and we need to add them together. And we also have to remember how addition kind of works at a binary level, right? So in a base 10 operating system, or base 10 system, like numbers that you and I would count in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20. That's how you count, I'm pretty sure. Don't quote me on that. So, we would add two numbers together, especially if they had like a tens place or something like that. So if I took two numbers such as 19 and 11 to add them together, and we're going to add these suckers together, then, we would start on the right-hand side, we would get 0 there, and we would carry the 1. So we would carry a 1 to the tens column to get 3 to get our answer of 30. And that carry right there, addition, dead air, hello, mods, fill in some sound instead of me just silently typing in letters there. We'll fix that in post. No, we won't. Okay, so I wanted to add some keywords here because I wanted to show y'all logically where we are going. So this is an example in base 10, right? And we're not going to be working in base 10. We're going to be working in base 2, aka binary, 0 and 1. But I wanted to remind y'all at a fundamental level some terms, what it looks like when we add two numbers together. So, I mean, this would be a plus sign down here, whatever. But, we have an input A and B. We add them together, and we get 30 as the answer here. Now, remember what I talked about in this base 10 setting. When a number gets to 9, it ticks back to 0, and we add a 1 to it. So that's where we got the 0 down here. And then we carry over a 1 to the next tens column, and you add that in there. So that carry is an important concept. If we all probably do this mentally, and we may not think about the terms or like the fundamentals of how it works. This is what it's going to have to do also in binary. We're going to have to add two numbers together in binary and know how to carry a 1 whenever we add two 1s together, right? Because in binary, if you add two 1s, you get a 0, right? And then you have to carry that 1 to the next column, and then so on and so forth until it winds up where it needs to be. The same logic happens here in binary. So remember, A and a B and a carry, and that's all we need to know. So that's what it looks like in regular arithmetic. Now let's actually code this out. Again, I don't expect y'all to know this, but follow along, write it out, and also write out these comments along with me as I attempt to show you the iterative process of how this works. So, and I'm going to laugh if I get it wrong, even though I practiced this before. So we are going to run a loop because we're going to have to be basically calculating our carry as many places as it needs to go over. And because this process is potentially an undetermined number of iterations, I'm going to choose to use a while loop instead of a for loop. We're going to be doing something with the value of b. So as long as b does not equal 0, we're going to continue running something. And then once this iteration is done, we're going to return a as our function. So clearly a will be the number we're going to be calculating as the sum of these two numbers. So from here, I need to do something interesting. I'm going to calculate something called the carry, and that's going to be done with the operation of a and b. So if you recall in our AND gate diagram, typically that's what it looks like. It looks like this little bullet thing here. We take a and b and return a and b. Remember, that's like our example, our analogy from previous videos of a very specific or strict security guard at a club. Only if bit and byte both have a VIP pass are they let in. So 0 and 0 get 0, 1 and 0, or 0 and 1 both wind up 0. The only way we get a 1 from an AND gate is if both inputs are 1. So that carry is going to be exactly that. It's going to be calculating to what place our carry is going to be, well, carried on over to for each iteration. Then we're going to be adding, basically calculating our sum without the carry. So if this is going to be carrying our carry, we need to do the sum without the carry, meaning we are going to take A and XOR it with B. So this is sum, this is our carry calculation, as the variable name implies. Then we have our sum without the carry. That's what's going to happen there. So remember our XOR, this is one of my very first ones I covered, a little bit more complex than the rest. It is this bullet with an indent and a line at its butt right there. That's what it looks like. A and B, A, XOR B, or exclusive OR is what it means, right? So again, this was like at a crossroads. It basically gets us to make sure that it is only happy if bit and byte take unique directions. If bit and byte decide to stand still or go in the same direction, it's like, nah. Y'all have to take unique directions at a crossroads. So bit and byte stand still? Sorry, that's not unique. That's a 0. Bit and byte go in the same direction? That's also a 0. Nah, that don't work for me. Bit and byte go in unique directions apart from each other? You're good. That means it's a 1 as a value from our XOR operation here. Okay? That's what a XOR does. Unique OR. And then B is going to be a carry left shift 1. Shift carry for next iteration to prepare basically, hey, as the 1 gets carried across, because remember, in binary, the carry will be a 1. So a 1 and a 1 get a 0, carry the 1 to the next column. Basically, we have to left shift the carry as far as it needs to go. So, of course, I deleted it, but back in our other example where I did 19 and 11, right? Where I did 19 and 11 added together to get our answer of 30. Remember, I did a 1 column over carry of a 1, right? Basically adding a 10. So that carry over, I did 1 time just by hand. But imagine binary having to do it 5 or 6 columns. That is the idea behind the carry left shift 1. So again, this is the code here. Believe it or not, we have already solved it with this code. I'm going to go ahead and console log add without plus. Let's do a 5 and a 3. Save it, and we get 8 as our output. It successfully worked. So if this still doesn't make sense, it's okay. It didn't make sense to me either until I wrote out each iteration of how this might work. So we're going to do that here together. I wanted to get to the code as fast as I could. Normally I've been, of course I finish it after the 11-minute mark. I started coding before the 10-minute mark. It's a personal goal to try and get to code faster and explanations later. Oh, and don't forget left shift is fairly straightforward. It basically will take an input and shift it to the left. So basically, it'll add a 0 at the beginning of the binary number, and it will shift all the other bits 1 spot to the left and blowing up whatever's on the left-hand side if it needs to or whatever. So basically, just think of it like a conveyor belt that's adding zeros at the beginning and shifting everything to the left by however many positions you specify after the operation. In our case, we're moving that 1 over to the left over and over and over again in our carry. So there you go. Now, let's actually see this thing in action, and it will probably make a ton more sense. So let's try and make this fairly legible. So when people look at my comments in CodePen later, they can see our thought processes of how we got here. So basically, we're going to be acting as the computer and breaking this down to try and visualize it. I'm going to laugh if I get this wrong, but it is what it is. I practiced this, and I should have written it down for notes, but of course I did not. So we're doing it live here, folks. All right, so we have our A and our B values, which is, the integer 5 and the integer 3. I'm putting them in parentheses because that's not what we're focusing on. That's what they are currently as our first iteration for A and B. But we know if that's 0 in binary, right? If that's 0 in binary, then that's 1. That's 2, which means that's 3. So technically, 3 is just 1, 1 in binary. So if we're going to do 5, that means we're going to have, that's 0, 1, 2, 3, 4, 5. Pretty sure that's correct. Yeah, so 101 is 5 in binary. And as we know in binary, leading significant 0, the most significant bit is that 1, but the 0 up here, we can add as many zeros in front as we want, and we won't be changing its value. So technically, I'm just adding that 0 up front of the 3 just to make sure the number of bits match up for our logic that we're going to be running here. So that's what we're looking at as our inputs. I'm going to make it a bit bigger here. This doesn't need to be as big. Or doesn't matter. Okay, so there's our first iteration. It's starting out with an A and a B of 5 and 3, which are 101 and 011 as our binary values. So the first operation that we do is calculating our carry, right? And that was the logic of A and B in our AND diagram. Remember, strict security guard will only let A and B bit and byte, or our 2 bits pass if they both have a 1. So let's go ahead and expand A. Let's go ahead and expand B. Let's go ahead and these suckers together. 0 and 1 one person's missing their pass, so nope, one person is missing their pass. They both got a pass in this column, and there is our carry. So if you even look at this right now, the 1 and 1 would get us a 0, and it would carry the 1, right? That's what would happen. So now we know we have a 1 carry, and then when we actually shift this to the left, oh, that's how the column is going to work. So this calculates the carry, and then the left shift 1 is going to move it over to the next column's place for our arithmetic operation. So hopefully you can kind of already see how this is being done. This calculates the carry. The left shift will move it over to the next column for the next iteration, etc., etc., etc. All right, so that's our carry calculation. Next, we reassign A. Important to remember. We're going to reassign A of A XOR B. So this is actually the arithmetic part, the sum of the two numbers, but without the carry. So here we go. This is going to be 1, 0, 1, 0, 1, 1. Those are our two inputs. We haven't reassigned A or B yet, so they're the initial two values, right? Same thing. Then we're going to XOR these together, the XOR operators, that up caret right there. So remember, this is exclusive OR. They have to be unique values, right? Otherwise, they get us zeros. So the first column has unique. The second column is unique. The least significant column, the two ones right there we're looking at, are both the same, which means we get a 0. So this reassigns to A as that value right there, okay? Next, we are going to reassign B to be whatever the carry currently is and left shift it by 1. If we scroll back up to the carry, which is right here, just so we can visualize a bit easier, our carry is 0, 1, 1, and we're going to left shift that 1. So what we're looking at here is we're going to take 0, 1 like that, basically add a 0 in front of it and move the left over 1 position. So basically we just shift that left over 1 and stick a 0 behind it, and that is our new B value. And just to be consistent, I've been doing spaces in the binary values on all these, so we're going to go ahead and just kind of expand it out to be consistent. So there you go. There is our first iteration. And our check is, remember, B does not equal 0. Is that the case? Well, in our case, B is 2, which is 1, 0. So yeah, B is currently 2, which is not 0, which means it's true, which means it continues the loop. Yeah, that makes sense. B is definitely not a 0, which means it continues the iteration. So we're going to move on to the next iteration, which is iteration 2. Okay? Here we go. So there's R2. R2. All right. So we have our new A and B right here. So we'll go ahead and write 1, 1, 0 for A, 1, 0, 0, 1, 0 for B. So our iteration 2 starts with these two as our A and B inputs. So same thing, let's calculate our carry, which is going to be A and B. So we're going to do 1, 1, 0, 0, 1, 0, and I hope this is correct. This seems right so far. I really should have written this down. Oh, I'm sweating bullets here, guys. Guys and gals, your boy's sweating bullets. Oh, God. Okay, so we have and. Nope. Yep. Nope. Wait, that's a yup, right? No, it gets us 0. What am I kidding? Yeah, they're the same thing. It gives us back the same thing. All right, so there's our carry. And yeah, it makes sense that our carry right here, these two will add together, and that's a 1 for our carry for sure, because these two added together would get us a 0 and then carry 1 to the next column, which our left shift should do for us. So that's our newly calculated carry. And now we need to do our reassignment of A XOR B, so the actual arithmetic operation of our numbers. There we go. So the actual arithmetic, remember exclusivity. Yep, nope, nope. So that is our new calculation of our value A right there in this particular thing. Remember, the XOR is exclusive OR. So if they take opposite roads, that's a good sign. If they take the same roads, nope. If they stand still, that's also a nope. So there we go. Now our next calculation was reassigning B to be whatever the carry was, left shift by 1. Our carry is 0, 1, 0, left shift by 1. We get 1, 0, 0 by, again, putting a 0 at the beginning and blowing up that leading 0 and moving the 1 on over. That is our new assignment of B. That is the value of 5. Because 1, 0 is 3, 1, 1 is 4, 1, 0, 0 is 5. Well, my input was 5, wasn't it? That doesn't seem, hold on. Did I mess something up? There's no way. No, that's 4. Because 5, That's 3. Yeah. Oh my god, that's 3. This binary stuff is killing me. Because that's 0, 1, 1, 2, 3, 4. Something's wrong here, isn't it? No! 5 is 101, so that would be 4. It's 4. What am I doing? Because that's 3. Because that's 2, 3, 4. Oh my god. B is 4. B is 4, which is definitely not 0. Because remember, our while loop ran this as our terminating condition. So, is 40... This 4 does not equal 0. It's true, so it keeps going. Because we got a 4 and not a 0. So it's going to continue to iterate. Which means, you guessed it, to the next iteration we go. So on iteration 3, we have an A of 100. So 100 is our A input. 100 is our B input. There we go. And we continue the process. So we're going to do our carry calculation, which is A and B. Hopefully you're having as much fun as... I mean, this is, even though I'm stressed out about getting the numbers right, this is fun. So here we go. We have our carry of A and B. So we're going to do our expanded numbers here so I can visualize this for y'all a bit easier. And our AND logic. Yep. Nope. Nope. There you go. That's our carry and B. So that's our new carry. So as you can tell, our carry has one more space because when we add these two columns, that gets us a 0, carry the 1s. That's our current carry, and we're going to left shift it on over to the next available bit. Next, we're going to recalculate and reassign a XOR B, which is our arithmetic operation without the carry yet. So our two numbers are both that right there. We're going to XOR them together. Remember, uniques only. And you're like, well, that's an odd answer, Luke. I know, but continue with me, because technically it's the correct answer without the most significant bit added to it yet. So, okay, that's our arithmetic operation without the carry, which is correct, believe it or not. I'm pretty sure this is right. This looks right so far, just by staring at it. B is going to be our carry left shift 1 in this operation. So, to reassign B, we're going to take our 100, left shift it by 1, which means, now we're not going to just huck the leading significant bit, which is a 1, into the garbage. We're going to shift it to the left and add a 1 at the beginning of our value here. So this is our new B value. Now this value right here is not 0, which means the iteration process, you guessed it, continues. Let's go ahead and get our next iteration, which I believe should be our final iteration here. So there's our 4 right here, iteration 4. Our inputs are 0, 0, 0 for A and 1000 for B, or 1, 0, 0, 0 for B. Okay, this is our next iteration. Continuing our logic, carry is A and B. We're going to do 0, 0, 0 for A, 1, 0, 0, 0 for B, and AND them together. Because their bits don't match, we have a 0 up here. I can just add a leading 0 and not have it alter anything on the actual value of the number. But remember our AND, so we get a carry of 0, because guess what? We are done carrying in this arithmetic operation. Remember, each step of the carry calculated where 2 bits together would carry over to the next bit, the next significant bit. In this case, we are done carrying in this iterative process, so our carry winds up as 0. Yay! And then finally, we're going to get our A, which should be our return value. We're going to reassign A to be the arithmetic operation of A XOR B. So we're going to get 0, 0, 0, and remember the 0 I'm adding just to make our lives easy. Our ampersands, nope. We get our XOR gate now. Uniques only. Okay, so that's our new A value. Then we're going to get our new calculation of B, which is our carry left shift 1. Our current carry is a bunch of zeros. Left shift those 1, and we're going to get a bunch of zeros anyway. It's not going to add another magical 0. I mean, it's going to shift everything over by 1 position, but there's nothing left to carry, and that's 0. So our B is not equal 0 check is now true because it is equal to 0, or rather it's not, it is equal to 0. So the loop terminates and returns A, which is 1000. So returns A, which is 10000, which should be 8 in binary, right? Yeah, because that is, I know 1000 is 8 in binary. And there you go. That is our answer. It returns 1000 in binary, which is indeed our 8 value. Whoo! Normally I do one or two, like 2 or 3 of these iterations to show you how it works. But because it takes so long to kind of go step by step, I encourage you to try 2 other small integer numbers on your own and paste in the comments your own version of this iterative process. Paste how it winds up with 2 different numbers and show me how you did it, or show me this, like the syntax or the context of how you do that. Get in the comments and paste a 2 different set of numbers so you can understand how this works, and show me your way of doing it. And if it's just like mine, that's also fine. And let me know, because I think this is really cool to understand how it does, how it works, right? But yeah, that's the answer. Returns 1000, which is 8 in binary. That is our answer. So back up to the code that did all this, remember? There you go. And you know how I memorized this by heart, this 3 lines of code with these bitwise operators, is because I wrote out in comments this crazy iterative process. So I wrote out the AN, B, A, XOR, B, carry left, shift 1 over and over and over again, and I began to memorize how the code actually looks. So this, like I said, is how a computer works at the most foundational level. As we learn about bitwise operators, we use the Christmas string light analogy, turning on multiple lights on with an AND, different ones on with an OR, unique ones only with a XOR, or moving the Christmas string lights to the left or right with the left and right shifting operators. There's a lot of cool things you could do with this, and you begin to understand more and more about how that little chip, that CPU, that square that for those builders out there crack into their motherboards, how that thing is actually operating underneath the hood. So, in terms of Big O, this thing is, as always, I mean, we're not doing anything special here, so it's back. Time and space of Big O of, you guessed it, 1. I mean, there's nothing happening here. The time complexity is determined by the number of iterations the while loop's going to run. But in each iteration, the carry is left shifted by 1. The operation effectively halves the value of B in terms of the highest set bit, rapidly converging to 0. So for our typical 32 and 64-bit integer systems, the convergence happens in a constant number of steps, right? It's bound by the number of bits in the integers, right? It's bound. It's a constant. 32 or 64 bits, there's no choice. So because it's not dependent on the input size, you would think because there's an iteration, it'd be like O of n, which is not. It's rather bound by a constant, the bit length of the integers, which means the time complexity is big O of 1. So again, that's the big takeaway. You would see a loop, and your first inclination with big O would be like, oh, if there is a loop, we would think big O of n. But that's not the case, because the input is set, right? It's either 32 or 64 bits every single time. No choice, right? Because remember, that's how they're stored in our computers underneath the hood, right? They are stored as 32 or 64-bit integers. So it's a big O time of 1. In terms of space, it's determined by any extra space aside from the input the function might use. We have that constantly fixed carry. We have to, an A and B we calculate there. No recursive calls, no dynamically allocated data or anything like that. Like I'm looking at my other monitor to like look at myself pointing at the code, which is what I'm doing here, even though it conveniently looks like I'm looking at the code, right? It's like working in 3D space here. Again, the space used doesn't scale to the size of the input. It remains constant, so the space complexity is also a big O of 1, just a flat line at the bottom, right? No big deal there. So, I mean, in terms of why this is cool, I mean, come on, just look at it. Don't you feel cool writing this instead of A plus B? It's so much cooler. It highlights that in exploring the fundamentals of computing, right? It's not just academic. It reveals exactly how your CPU is working beneath that CPU cooler in your laptop or your desktop that you built. Bitwise operators are these unsung heroes. They are super underappreciated, and they are so elegant when you understand how they begin working. So I hope everyone in the comments has had as much fun as I have diving into these Bitwise operators. I think I have one more algorithm on my books before I cover my favorite usage of these in the real world, which is the Quake 3 algorithm, the fast inverse square root. The ability to think outside the box with Bitwise approaches, again, it's unlikely you're probably going to encounter a specific test that will use them in an interview, but if you can find a way to just talk about them and show your understanding, shows how well you can think outside the box about manipulating data at a bit level. That coincides with my point that I was making to my buddy. Like, I was driving with a developer buddy, hanging out with him this past weekend, and I was talking about the wow factor that this could have in an interview should you find a practical usage of it in an interview. Oh my goodness, you will blow them away by being able to discuss this and like take them through like the comment process like I did of how it works as well, and you will look so good in an interview, trust me. And I was joking with my buddy Andrew, also posts videos on this channel. Make sure to like, comment, subscribe, do the YouTube stuff, about how we could shoehorn this to an interview, and he was like, "Sir, you're applying for the website, the front end dev position at an Arby's." And I was like, we can calculate the total of your Arby's order by using this instead of returning with a plus sign, right? So you can sum an array of number values by using this function to tally the number for each addition of the running total of our shopping cart plus the next price. I was laughing maniacally because I was like, we're going to shoehorn this in wherever we can. But in terms of practical applications, graphics, optimization, hardware control, networking, cryptography, all your normal suspects and things like that. So yeah, that's a wrap on today's episode. We've journeyed through the bits and bytes of addition, unraveling how computers add numbers together, right? I really found this fascinating, and I hope you found it as fascinating as I did. So hit the like button, subscribe to our channel for more coding adventures, have thoughts, questions, comments, your own Bitwise wizardry if you ever actually had an interview where you got to use this, or a case where you think this might be useful. Again, paste your comments of your own inputs of add without plus and show the world that you understand how to do this as well. So I love hearing from you guys. So remember, it's not just about learning syntax, it's about thinking creatively and understanding the why behind the how. So keep exploring, keep coding, and as always, stay curious. Bye.